So by now we have learned what an electric charge is, and what happens if you have an electric charge which is at rest. So we have this positive charge here which is at rest, then this positive charge, it will produce an electric field around its space, and that electric field is represented by electric field lines. So for the positive, it's always away, it's pointed away from the positive charge. And we have found out also the electric field intensity at any point P, which is at a distance r from the point charge say Q, and that electric field, or the strength of the electric field at this point, is given by E, and this is equal to 1 by 4 pi epsilon naught Q by R square. So this is the electric field intensity due to a point charge plus Q. We have also found out the electric field intensity due to a system of two equal and opposite point charges, which is an electric dipole. So we have an electric dipole here. So this is a system of two equal and opposite point charges. So this is your electric dipole, minus Q, and we have plus Q, and we have found out the electric field at a point on the equatorial line here, and at a point on the axial line here. By using this formula, we have found out the electric field intensity at this point and at this point. Okay, so these are the electric field intensity due to point charges. Here we have a single point, and here we have a system of two point equal and opposite point charges. But what happens if we have a charge distribution, not just a point charge, but if the charge is distributed along a wire or along a line or across a surface? So what if we have this charge distribution here? Let's say this is a wire, and let's say these charges are distributed along the wire. Then what will be the electric field intensity at this point P? And what if we have a surface here, and if your charge are distributed across the surface? Then how will you find the electric field intensity at this point P? Say which is at a distance say r from this line distribution, and at distance r, perpendicular distance r from this surface distribution. Now this is known as linear distribution, linear charge distribution, and this is known as surface charge distribution. So if you are required to find the electric field intensity at this point and at this point, then we'll have to use the superposition principle, which in this case will be complex, and it will be a very different method. So we'll have to choose another method which is much more easier than this superposition principle. So in order to use that method, we'll have to introduce the concept of electric flux and Gauss law to find the electric field intensity at this point and at this point. So the other method is this superposition principle, and this method which we are going to do in this lecture is by using the concept of electric flux and Gauss law. So you'll have to use both these concepts to find the electric field intensity at this point and at this point. Now first I'll just give you a definition of this linear charge density, lambda. So here we have linear charge density. This is denoted by lambda. Right, so suppose you have here Q is a charge distributed on this wire, along this wire. So we have plus Q. This is the charge distributed along this wire, total charge on this wire. And say the length of this wire is L. Then this lambda is defined as the charge per unit length. It means that in this unit length, say 1 unit, how much is the charge distributed in this 1 unit length? It is lambda. So lambda is the linear charge density, is the charge distributed per unit length, which is this one. Okay, the charge distributed in this 1 unit length of this wire. So that is known as linear charge density. Then another definition is the surface charge density. Surface charge density, which is denoted by sigma. And this surface charge density is the charge per unit area. Suppose here Q is the charge distributed on this area. Suppose here we have plus Q. This is the charge distributed on the area. And let this area be A. Then this surface charge density is the charge distributed per unit area. So if we have a unit area here, okay, so this is 1 unit area. So sigma is this charge distributed in this 1 unit area. So here we have 1 unit here, 1 unit here. So surface charge density is the charge distributed in this small area here, okay, per unit area. So these are the two definitions. One is for linear charge density and the other one is for surface charge density, which we are going to use in the finding the electric field intensity at this point P and at this point P due to the surface charge distribution, and here due to the linear charge distribution. So let's define what is electric flux, and let us see what is the statement of Gauss law. So electric flux, it represents the total number of electric field lines crossing an area in the direction which is normal or perpendicular to the area. So if we have an area here, so this is the surface area. Let's say it's A, and if your electric field lines, they are crossing this surface area in this direction. So these are the electric field lines crossing the area normally. Then the electric flux represents the total number of electric field lines crossing this area in a direction which is normal to the area. So in this case you can see that here this field line, it crosses the area A at an angle which is 90 degree to this or normal to the area. So that is the electric flux. The definition of electric flux, it represents the total number of electric field lines crossing an area in a direction which is normal or perpendicular to the area. Okay, but in order to measure the electric flux, which is denoted by phi E, so this is your electric flux. Electric flux is denoted by this symbol phi E, and it is defined or measured as the dot product of the electric field vector and the area vector. So E dot A, that is the definition of your electric flux, is the dot product of the electric field vector E and the area vector A. And E dot A, this is equal to the dot product of two vectors is equal to E A cos of theta. Theta is the angle between the area vector and the electric field intensity vector. So for example, here your E vector is in this direction, and the area vector, see the area vector, the direction of the area vector is always normal to the area. So your area vector will be in this direction. So this is your A vector. So you can see here that both these area vector and this electric field intensity vector, these are in the same direction. So in this case, this angle theta will be equal to 0, and cos of 0 you'll get just in this case you'll have E EA cos of 0 degree, and cos of 0 will be equal to EA. So the electric flux here will be equal to E into A in this case. But this does not always happen. For example, if we have a surface area, again here, A, then your electric field lines this time will not cross the surface normally. For example, your electric field lines this time will cross the surface in this direction. So these are your electric field lines, and this is your surface area A. Now in this case your area vector is always normal. Remember this one, A vector, this is always normal to the area. This is your A vector, and as you can see here, the electric field line is not crossing the area normally or in the direction which is normal to the area. In this case, you can see the E vector, it's making an angle with this A vector, and that angle is given by this one, theta. So this angle here is your theta. Okay, so in this case, what you do is you'll have to split or resolve the components of the electric field E vector. So you'll have to resolve one which is normal to this surface area A, and another one which is parallel to the surface area A. Okay, or in other words, one is in the direction of the area vector A, and the other one which is in the perpendicular direction with the area vector A. So on resolving, you'll come across this formula. Okay, so you have E vector. One, you can resolve this one in this direction. I'll drop this one. This is your theta, remember this one. So here we have E. This is along the surface, and another one is here, which is in the direction of the surface. And this component is neglected because this one does not cross the area, and you'll only have to take this component here, which is in the direction of the area vector A. So only this component which crosses the area vector or the surface area A is taken to be measured as the electric flux. Hence you have your phi E to be equal to E dot A and is equal to EA cos theta. Okay, so in the earlier case, I've shown you the electric field to be equal to, or electric flux, I mean, to be equal to EA when the electric field line crosses the area normally. Now what happens if your electric field lines does not pass the area? Instead it just glides through the area. So in this case, your area vector will be in this direction, normal to the area, and your E vector is in this direction. So here in this case, the angle between the E vector and the area vector A is 90 degree. So in this case, your phi E, this will be equal to E A cos of 90 degree. So cos of 90 is equal to 0. So the electric flux is equal to 0 in this case. You can see in the diagram also, there's no electric field lines which crosses the area. Okay, hence the electric flux is equal to 0. You can remember that electric flux represent the total number of electric field lines crossing an area, and in this case you see it's not crossing the area, hence your phi E mathematically will be equal to 0. And in the earlier case, we have phi E to be equal to EA, which is maximum. Okay, so the electric field lines in the earlier case, if we can remember, we have an area, and the electric field lines is crossing the area normally. So in this case, your phi E would be equal to EA, which is maximum in this case, and here it's 0, which is minimum. So there's another expression for this electric flux. One expression is this one, E dot A. There's another expression which we are going to use integration. Okay, so another expression for your electric flux. So here we have a surface area, say S. This is the surface area S, and your electric field lines is crossing this area in this direction. So this is your E vector, electric field vector. Now what we'll do is we'll select a very small area, elementary area ds. Okay, and this is a very small elementary area ds. If you sum all these area, you'll get the whole area S. Okay, so this ds, if you add in this direction, if you add in this direction, if you add in this direction, then you'll get the whole area S. Okay, and this ds can also have an area vector, which is given as ds vector, and it's normal. This ds vector, this is the elementary area vector, which is normal to this area or surface area ds. And let's say the angle between this E vector and this ds vector is theta. So theta is the angle between E vector and ds vector. So the electric flux through this small area ds, elementary area ds, is given by d phi e, and this is equal to, again, the dot product of electric field vector and this elementary area vector ds. So this is the electric flux through this small elementary area ds. If you want to find the electric flux through this area S, the electric flux through this area, then we'll have to sum all this area, or in other words, we'll have to, I'll use the proper words here, we'll have to integrate this d phi over the surface. So your electric flux through this surface S, and this is integration over the surface of this d phi e, and d phi e is E dot ds. So here we have integration E dot ds. Okay, so integration here, it means summation. You add all these small elementary area or small elementary flux through this small elementary area ds, you'll get the electric flux through the whole surface area S. So this is another expression for your electric flux. One expression is this, E dot A, simply E dot A. Another expression is phi E is equal to E dot integration over the surface E dot ds. Okay, so remember this ds vector is this area vector, and this ds here is this small elementary area, and this d phi is the electric flux through this small elementary area. And if you want to find the electric flux through this whole surface area S, then you have to integrate this d phi e over the surface, which is given as this one, integration E dot ds. So that's the concept of electric flux. Remember, electric flux represents the total number of electric field lines crossing an area in the direction which is normal to the area. And we can have two expressions, or it's can be defined as the dot product of the area vector and the electric field vector. And we have two expressions. One is E dot A and the other one is integration over the surface E dot ds, which is also known as surface integral. Now we come to Gauss law. Gauss law will actually give us the electric flux through a closed surface. For example, if we have a point charge plus Q, then you know that for this positive charge, the electric field lines is away. Now what you do is you place this point charge inside a sphere. Okay, so I cannot draw a three-dimensional sphere, so this is represented by this circle here. But this is actually a sphere, inside a sphere, or inside a ball, for example. Okay, so this charge is inside a ball, and this sphere, it has a surface area. And since these electric lines, they are crossing the surface area of this sphere, which is this one. Okay, I cannot show you here because again the sphere is I cannot draw a three-dimensional sphere. Okay, so it's represented by this circle. So here your electric field lines, they are crossing the surface area S, and in this case you see that the surface area of this sphere is actually a closed surface. So the electric flux through the closed surface is given by Gauss law, and that electric flux, according to Gauss law, is equal to 1 by epsilon naught times the charge enclosed by the closed surface, which in this case is Q. So this is the electric flux through a closed surface, which is given by Gauss law. So this is your electric flux by using Gauss law. Remember, the surface has to be a closed surface. For example, if I take this piece of paper, now you can see this is an open surface. Okay, so this surface is an open surface, but once I do it in this way, it becomes a closed surface. So this now becomes a cylinder, which is a closed surface. So it can enclose anything inside it. Okay, so this is a closed surface, and this is an open surface. So electric flux, according to Gauss, using Gauss law, it applies only for closed surfaces. So if this surface encloses a charge inside it, then the electric flux through the closed surface, is given by this Gauss law, which is Q by epsilon naught. Q is the amount of charge enclosed inside this surface, a closed surface. Okay, so in this case I've given an example of a sphere, and this charge is inside a sphere, okay, inside a ball. Okay, so you should be clear with this one. It applies, Gauss law applies only for closed surface. Okay, electric flux through a closed surface, and this phi E by definition is equal to E dot A. So E dot A is equal to Q by epsilon naught. Or another expression is this one, integration over the surface E dot ds, this is equal to Q by epsilon naught. And in this case, since it is a closed surface, we'll have to add this small symbol here. Okay, so this one means integration over the closed surface, E dot ds, which is the electric flux, and this is equal to Q by epsilon naught. In the earlier expression, there's no circle here, okay, because it is an open surface. So this circle here is because of a closed surface. The electric flux through a closed surface is equal to Q by epsilon naught, and Q here is the charge enclosed by the closed surface. So this is Gauss law. So we'll have to use these two concepts. One is by definition, electric flux by definition. Another one is by Gauss law. So these two, they are the same. Okay, so if you want to find electric flux through this closed surface, you can either use this one, which is equal to Q by epsilon naught, by using Gauss law. Okay, so this Q by epsilon naught is by Gauss law. This integration over the surface E dot ds, this is by definition. Both these two, they are equal. So if you want to find electric flux, you can use the definition E dot ds or E dot a, sorry, and Gauss law. If the charge is inside a closed surface, and if the electric flux is through a closed surface, okay, not an open surface. Okay, remember that it does not apply through Gauss law, does not apply to an open surface. So these are the two concepts of electric flux and Gauss law, which we are going to use to find the electric flux. One is, to find the electric field intensity due to an infinitely charged wire. Okay, so we're going to use the concept of electric flux and Gauss law to find the electric field intensity at this point P, which is at a perpendicular distance R from this infinitely charged wire. So we are going to use this formula. This is the formula which we are going to use to find the electric flux, to find the electric field intensity at this point P due to this infinitely charged wire. And another one is when your charge is distributed on the surface of a sphere, okay, not inside the volume, not inside the sphere, on the surface, say, of a shell. So if your charge is distributed on the surface of a shell, then what will be the electric field intensity at this point P, which is at distance R from the center O of this shell. So in order to find the electric field intensity at this point, again we'll have to use this concept here, electric flux and Gauss law. And again, if we have an infinitely charged sheet, okay, this extends to infinity, so plus Q, this, remember, extends to infinity. So if you want to find the electric field intensity at this point P, which is at a distance, let's say R, perpendicular distance R from this sheet here, thin sheet, then again here also we'll have to use this concept of electric flux and Gauss law. Okay, so in the next session I'll find out the electric field intensity first due to this infinitely charged wire, then due to this charged shell, and then due to this infinitely charged thin sheet. Okay, so we'll continue in the next session.